Well, welcome to the last lecture of this course. We have made it to the end of the course, and you know what that means, don't you? Comprehensive final, everyone's favorite topic. So to help you prepare for that, we are going to do a long series of just question review. So this is no new material. We're just going to work through a bunch of questions in kind of a seemingly random order, and let's see how you do. So there shouldn't be anything new, and we're just going to review some of the skills that you have developed throughout this entire course. So let's begin with the first question. All right, the first question has to do with a nasal solution, and we are trying to prepare it. And so if you look on the prescription on the top right, there are three ingredients. So the first ingredient calls for tetracrane hydrochloride at a concentration of 0.75% weight per volume. And then the second ingredient is epinephrine hydrochloride at a concentration expressed as 1 to 4,000. So we have a ratio strength of 1 to 4,000. And lastly, cocaine hydrochloride used in a concentration of 3% weight per volume. And then the last ingredient is to use whatever amount of sodium chloride and then water, obviously purified water, to make the final nasal spray isotonic. And it says QSAD up to a total volume of 30 milliliters. And you'll notice that I have also provided you an E value or sodium chloride equivalent value for each of the three ingredients. So clearly we're wanting to make an isotonic nasal spray that contains three active ingredients and enough sodium chloride so that we can make the final solution isotonic, and it has a volume of 30 milliliters. So we're going to work through this question kind of one step at a time. So the first question, part A here, says you need to prepare 30 milliliters of this formulation. How many grams of each of the active ingredients will you need? Okay, it's pretty straightforward. We're going to use our volume of 30 milliliters and our concentrations for each of the three different ingredients. Part of the problem being, though, our concentrations were expressed in different ways. So let's do this one at a time. Our first ingredient was tetracane. So let's take the 30 milliliters, which is the volume we're going to prepare, and multiply it by its concentration, which was given to us as 0.75% weight per volume. And hopefully by now you'll be able to convert that to an expression of 0.75 grams per 100 milliliters, since that is what by definition a percent weight per volume is. It's grams per 100 milliliters. So if we multiply that out, our units of milliliters will cancel, and 30 times 0.75 divided by 100 gives us a final value of 0.225 grams of tetracane. All right. Our next ingredient was epinephrine. So again, we'll start with our final volume, which is 30 milliliters, and multiply it by its concentration, which was given to us as a ratio strength of 1 to 4,000. But we remain calm because we can just express that ratio strength as a 1 gram over 4,000 milliliters. Since it's weight per volume, 1 to 4,000 is 1 gram per 4,000 milliliters. If we multiply that out, again, milliliters cancel, and 30 times 1 divided by 4,000 gives us a numeric value of 0.0075 grams. And our last ingredient was the cocaine, and we'll start with, again, the 30 milliliters times its concentration, which was 3%, meaning 3 grams per 100 milliliters. Again, milliliters cancel, and 30 times 3 divided by 100 gives us a final numeric value of 0.9 grams of cocaine. So as you can see, what we've done so far in this first part of this question is determine the actual weight of the three of our active ingredients. The second part of this question, part B, says, you have on hand the following solutions: tetracane hydrochloride 2%, epinephrine hydrochloride 1 to 1,000 ratio strength, and cocaine 0.6%. How much of each solution will you need, and how many milliliters of water also will you have to have in the end? So this is kind of a continuation. Now that we know how much of each of our active ingredients we need, we're going to need to calculate the volumes of the solutions we're using to obtain those active ingredients. Since each of those active ingredients will come from a stock solution of some sort that we're using, let's calculate how much we need. Okay, so we'll start with tetracane, and I'll remind you from our answer from part A was that the amount of tetracane we needed, our target was 0.225 grams. And again, since we're starting with a 2% weight per volume solution, we can multiply by the fact that there would be 100 milliliters over 2 grams. That way grams cancel. If we multiply that out, we'll see that the volume of that 2% solution we need for the amount of tetracaine we require would take 11.25 milliliters. So that would be the volume of our tetracaine. The next ingredient let's do is our epinephrine. And I'll remind you, our target was 0.0075 grams. And let's multiply it times, again, its concentration, which was a ratio strength, but we'll watch our units here. And we'll say that we can multiply times 1,000 milliliters over 1 gram, because a 1 to 10,000 means 1 gram per 10,000 mils. So we'll multiply with 1,000 mils on top over 1 gram. Grams cancel, and our final value there would be 7.5 milliliters. Our third ingredient was the cocaine, and our target was 0.9 grams. We'll multiply it by its concentration, which was 0.6%. So we'll multiply by 100 milliliters on top over 0.6 grams in the denominator. That way the grams will cancel, and our final value there when we multiply across would be 1.5 milliliters. So we now know the actual volumes for each of our ingredients that we're going to need to combine to make the right concentrations for our active ingredients. However, we haven't yet determined the final volume of water, because remember, to get the right concentrations, all of our ingredients would have to be in a total volume of 30 milliliters. So to determine the amount of water we need, we simply start with our final target, which was 30 milliliters, and subtract each of our active ingredients. So we'll take 30 milliliters minus the 11.25 milliliters for the tetracaine, minus 7.5 milliliters for the epinephrine, and minus the 1.5 milliliters for the cocaine. We subtract all of that out, and we said our final value that we need for water would be 9.75 milliliters. And that's the answer to part B. So part C of this question says, how many milligrams of sodium chloride are needed to make the final solution isotonic? So we finally came down to our isotonicity question. And to do this, what we're going to do is we'll look at the prescription we were given, sodium chloride equivalent values, or E values. So the process we're going to take here in a minute is to convert the weight of each of our active ingredients to an equivalent weight of sodium chloride. So we're not saying that those drugs have sodium chloride in it, but we're going to be able to convert the weight of our drug to an equivalent weight of osmotically active sodium chloride. Okay, and so let's do that, and we'll do that one step at a time as well. Starting with tetracaine, we know the amount of tetracaine we're going to have in our solution is 0.225 grams. We can multiply by its E value expressed as 0.18 grams of sodium chloride per gram of tetracaine. And that's kind of key in terms of what we've reviewed in this course. When you get an E value of 0.18, for example, you need to know the units. And the units for that would be 0.18 grams of sodium chloride per gram of drug. That way, as you can see here, when we do it for tetracaine, grams of tetracaine cancel, and we'd be in grams of sodium chloride. And lastly, for all of these questions, since we want to know milligrams, I'm going to go ahead and convert my final answer to milligrams. So simply I'm going to multiply my answer in grams, multiply my answer by grams, by 1,000 milligrams per gram. So the units of grams cancel, and my final units will be in milligrams. So if I do that math for tetracaine, I see my final answer would be 40.5 milligrams of sodium chloride. Let's do the same process for epinephrine. We're starting with 0.0075 grams of epinephrine, multiplied by its E value of 0.29 grams of sodium chloride per gram of epinephrine, so grams of epinephrine cancel, multiplied by 1,000 milligrams per gram, so units of grams cancel, and my final answer would be 2.18 milligrams of sodium chloride. That's what's equivalent to our amount of epinephrine. Third ingredient was cocaine, so we'll start with our 0.9 grams of cocaine times its E value, which was 0.16 grams of sodium chloride per gram of cocaine, so grams of cocaine cancel, multiply by 1,000 milligrams per gram, and our final answer there would be 144 milligrams of sodium chloride. Okay, so I have determined equivalent weights of sodium chloride for each of my 3 active ingredients. The next step is to know what my target is, though. How much sodium chloride do I need? Well, I'm going to base that on the fact that I know that an isotonic concentration of sodium chloride is 0.9%. Okay, and I know that if I'm going to compound 30 milliliters, then I can take my 30 milliliters times that concentration of 0.9 grams per 100 mils. Mils cancel, and I would be in grams of sodium chloride. Again, converting that target amount to milligrams by multiplying by 1,000 milligrams per gram. I see that I would need 270 milligrams of sodium chloride to make 30 milliliters isotonic. So my target amount of sodium chloride is 270 milligrams. So my last step is simply to take my target, 270 milligrams, and subtract each of my active ingredients. So I'm getting the 40.5 milligrams of sodium chloride from the tetracaine, the 2.18 milligrams from the epinephrine, and the 144 milligrams from the cocaine. So I subtract all of those amounts from my target, and I see what I still need to add is 83.32 milligrams of sodium chloride. So if I add that amount of sodium chloride to each of the the amounts that I need for each of my active ingredients, then I would have the equivalent amount total of 270 milligrams, which would be the right amount of sodium chloride to make 30 milliliters isotonic. And so that essentially answers this question and kind of solves this whole question for this prescription. I know how much of my active ingredients I need. Therefore, I've determined the volumes of each of my ingredients. And I'm going to combine those volumes with an additional amount of water and then also weigh and dissolve in an additional 83.32 milligrams of sodium chloride. And I'd have each active ingredient at the right concentration and with enough additional sodium chloride to make the 30 milliliters isotonic. Now, letter D is essentially the same question, but now we're going to fix the isotonicity not by using sodium chloride and the sodium chloride equivalent method, but let's use boric acid and the freezing point depression method. And you're going to use the same active ingredients and the same concentrations, but let's change the isotonicity calculation and use freezing point depression and boric acid. So the question says, how many milligrams of boric acid, again with its freezing point depression at 0.29 degrees, do you need to add to make this solution isotonic? Okay, so how do we provide this? Look on the prescription, and then now instead of E values, I've given you delta TF 1%. And remember, that means those are the values that produce a change in freezing point of a 1% concentration. So, for example, for tetracaine, we see the delta TF, that is the change in freezing point for a 1% solution, would be 0.11 degrees Celsius. So 1% boric acid reduces the freezing point depression. 1% concentration of tetracaine lowers the freezing point depression by 0.11 degrees Celsius. So, and we have those similar numbers for each active ingredient. So let's do these. And I'm going to solve all of these at the same time because they're all set up the same. So what you have to do is take your delta TF 1% and set it up as a proportion such as, for example, with tetracaine. As we just said, we get a 0.11 degrees Celsius change in temperature for a 1% concentration of tetracaine. So we can set that equal to some unknown X change in freezing point when we use the percent concentration we need, which is 0.75%. So when I solve for X, I see that my required therapeutic concentration of tetracaine will therefore lower the freezing point depression of my solution by 0.083 degrees Celsius. Let's go on to epinephrine. Its delta TF 1% is 0.17, which means 0.17 degrees Celsius change caused by a 1% concentration of epinephrine. And we'll set that equal to some unknown change in concentration given its percent. Now, I made a bit of a change here. I've gone ahead and kind of quickly calculated a 1 to 4,000, so 1 gram per 4,000 milliliters is the same as 0.025 grams per 100 milliliters. Therefore, it's 0.025%. So I've kind of quickly changed the concentration to percent since that wasn't the main emphasis of this part of the question. So trust me, 0.025% epinephrine is the same as our 1 to 4,000. Since that's our concentration now, we can solve for X and determine the freezing point depression caused by that concentration, which we see is 0.004 degrees Celsius. And lastly, let's do it for cocaine. We see that the cocaine delta TF 1% is 0.09, so that means 0.09 degrees Celsius for a 1% concentration of cocaine. Set that equal to some unknown change in temperature when we use a 3% concentration. Solve for X, and we get a 0.27 degrees reduction in freezing point caused just by the cocaine. Now, in this method, now that we know the individual changes caused by the individual ingredients, let's start from our target and subtract the individual effects. In the freezing point depression method, what you have to know is that an isotonic solution freezes at a 0.52 degrees Celsius temperature. So if our target is 0.52, let's subtract out the reduction in temperature caused by each of our individual ingredients. So 0.52 minus the 0.083 caused by the tetracaine, minus the 0.004 from the epinephrine, minus the 0.27 caused by the cocaine, gives us a remaining, that is a freezing point depression we still need to obtain, quantity of 0.163 degrees Celsius. So if we still need to obtain that amount of reduction in freezing point, what are we going to use to do that? We're going to use our boric acid. So let's go back and use our same sort of formula for the delta TF for boric acid and say that we were given that it produces a 0.29 degrees Celsius reduction for a 1% concentration of boric acid. We can now set that equal to the amount of reduction we need. What we need is a 0.163 degrees Celsius reduction. We can set that over to X, and when we solve for X, we would find the percent concentration of boric acid we would need to produce that reduction. And when we do that, we see we would need a 0.562% concentration of boric acid. So we're almost done, but the final question or the answer wants to be in milligrams of boric acid. So all we need to do now is take our total volume that we're going to compound, which is 30 milliliters, and multiply it by the concentration we just solved for, which was 0.62%, which means 0.562 grams of boric acid for every 100 milliliters. We multiply by that, and milliliters will cancel and will be in grams. And lastly, convert grams to milligrams by multiplying by 1,000 milligrams per gram. Grams cancel, and our final answer would be 169 milligrams of boric acid. So analogous to our answer for the previous part, which was for sodium chloride, now we could see with the same amount of active ingredients that we had before, instead of adding additional sodium chloride, we could simply add additional boric acid in the amount of 169 milligrams of boric acid, in addition to our active ingredients to a total volume of 30 milliliters, would produce an isotonic solution. And that is the final answer to this first question about the formulations for this nasal spray. All right. Our next question has to do with a prescription that calls for a veterinary antibiotic anti-inflammatory combination, what we call an otic ointment, which means an ointment that's going to be used in the ear. And again, I'll remind you this is actually a veterinarian product. So let's look at the prescription first. It calls for a combination of essentially 4 ingredients. Gentamicin, which is an antibiotic, we want 300 milligrams. And betamethasone, which is kind of an anti-inflammatory at 273 milligrams. Clotrimazole, we want 1 gram, and clotrimazole is kind of an antifungal. And lastly, tetracaine again at 1 gram. And tetracaine in this case is being used as kind of a numbing agent or to alleviate kind of pain and discomfort. And all of that's going to be mixed with enough propylene glycol, QSAD, to a total weight of 100 grams. All right. The only other thing I can notice over on the note below the problem, it says that the USP potency equivalent is no less than 590 micrograms of gentamicin per milligram of gentamicin sulfate. So keep in mind, what the prescription calls for is 300 milligrams of gentamicin, but in this first question, you're going to see here a little bit, our active source of gentamicin is actually gentamicin sulfate, because the question, letter A, says, how many milligrams of gentamicin sulfate would be needed to prepare 30 grams of this formula if the batch of gentamicin sulfate meets the potency requirement we just described. Okay? So a couple of things going on there. Not too bad. Where do you start with this question? It wants to know how much gentamicin sulfate in milligrams based off of 30 grams of this formula. So let's start off with the fact that we're going to be starting with 30 grams of this formula, which is for an ointment. So if I start with 30 grams of ointment, then what I need to do is look at the formula. And the formula tells me that I need 300 milligrams of gentamicin base, which I'll abbreviate GB here, gentamicin base, for a total weight of 100 grams of ointment. So I'm going to set it up and take 30 grams of ointment times the relationship of 300 milligrams of gentamicin base per 100 grams of ointment. That way my units of grams of ointment cancel, and I'm in milligrams now of gentamicin base. So the last step is, it wants to know how much gentamicin sulfate I need to provide that amount of gentamicin base. So looking up at my note, I was given a relationship that for every 1 milligram of gentamicin sulfate, there would be 0.59 milligrams of gentamicin base. Now I skipped a step where I converted 590 micrograms to milligrams. So realize there's 1,000 micrograms per milligram. So to convert micrograms to milligrams, you divide by 1,000. So 590 divided by 1,000 is 0.59, which is why I'm going to multiply this by the concentration expressed as. There would be 1 milligram of gentamicin sulfate over what it contains, which is 0.59 milligrams of gentamicin base. Units of milligrams of gentamicin base cancel, and my final answer, doing the math from left to right, would be 153, and the units would be milligrams of gentamicin sulfate, which is essentially the answer to part A. Going on to part B of this question, asks, how many milligrams of beta-methasone valerate with a molecular weight of 477 should be used to prepare 30 grams of this ointment? Keep in mind, I also give you that the actual formula weight for beta-methasone is 392. And I'll remind you, the formula up above there gives us the amount we need for just pure beta-methasone, not the beta-methasone valerate. So this is a perfect example where we have a active drug moiety, beta-methasone, contained within a larger compound, beta-methasone valerate. So to answer this question, we always want to establish clearly what is the moiety, what is the compound. So I'll remind you, in this question, the moiety is just pure beta-methasone. The compound is beta-methasone valerate. Okay? So the first step in doing this is to determine, essentially, the amount of moiety called for in the prescription. So the question wants to know how much beta-methasone valerate for a 30 grams of this ointment. So let's again start with 30 grams of ointment and multiplied by the concentration of beta-methasone given in the formula, which we said was 273 milligrams of beta-methasone, and I put a capital M here to remind you that means the moiety. The moiety is beta-methasone, so we have 273 milligrams of that moiety for every 100 grams of ointment. So now when we multiply that across, grams of ointment cancel, and we would be in milligrams of beta-methasone. That is the moiety, which says for 30 grams, I would need 82 milligrams of pure beta-methasone. The question then, the next step, is to convert that to the weight of beta-methasone valerate I'll need to use to compound this. So to do this, we're going to set up a proportion using the molecular weights. And we always do this as moiety over the compound. So the molecular weight of just the moiety beta-methasone was 392 on top. We'll put that over, or in the denominator, we'll put the molecular weight of the compound, which we said was beta-methasone valerate, which had a molecular weight of 477. So now that we have the ratio of 392 over 477, which is the moiety over the compound, I can set that equal to the weight that I do have as an expressed, which was 82 milligrams of the moiety beta-methasone over X. And when I solve for X, it will represent the weight in milligrams of an equivalent amount of the compound beta-methasone valerate. So solving for X, I see that my answer is 100 milligrams, which means that if I weigh out and use 100 milligrams of beta-methasone valerate, it will provide in my formula the equivalent amount of just pure beta-methasone moiety. All right, let's move on to our next question and topic that's kind of related to you calculating milliequivalents. And the question says, a patient has been taking 2 Oscal tablets per day, and each Oscal tablet contains 650 milligrams of calcium carbonate with a chemical formula CaCO3 and a molecular weight of 100.09. So part A says, how many milliequivalents of calcium is she receiving each day? Well, where do we start? Let's start with what she's taking. She's taking 2 tablets. So don't forget, let's start by saying, okay, 2 tablets. We'll start with 2 tablets, and then we'll multiply by the weight of calcium carbonate in each tablet, which we were given to be 650 milligrams calcium carbonate per tablet. Now tablets cancel, and we're in the milligram weight of calcium carbonate. Let's go ahead and convert that to the number of molecules of calcium carbonate by multiplying by the fact that in 1 millimole calcium carbonate, it would have a weight of 100.09 milligrams of calcium carbonate, since that is its molecular weight. Units of milligrams cancel, and I'm now in the number of millimoles of the calcium carbonate. Next, let's look at the formula for calcium carbonate, which is CaCO3. So there's actually just one calcium ion in every 1 molecule of calcium carbonate. So I'll multiply by the fact that there's 1 millimole of calcium ion for every 1 millimole of calcium carbonate. So now I convert from molecules of calcium carbonate to just molecules of the calcium ion. Lastly, to calculate the number of milliequivalents, I have to account for the valence. Looking at the charge or the valence on calcium, it's a positive 2. So there are 2 milliequivalents, 2 valence units. So 2 milliequivalents of calcium for every 1 millimole, for every 1 millimolecule of calcium. I get 2 milliequivalents. So I do that math from left to right. My final answer would be 26, and my remaining units are in milliequivalents of calcium. So essentially we're saying taking 2 of these Oscal tablets provides this patient 26 milliequivalents of calcium each day. Okay, going on to part B, says, this patient now wishes to switch to an ultra-dense calcium citrate formulation with the brand name of Citracal. Each Citracal tablet contains 950 milligrams of calcium citrate, with the formula given there and a molecular weight of 498.44. Essentially the question is, how many tablets would she need to take in order to receive the same number of milliequivalent dose of calcium as she was getting from the Oscal, which I'll remind you we just solved to be 26 milliequivalents of calcium. So how many tablets of the Citracal does the patient need? All right. Well, now we're going to start with our target amount of calcium, milliequivalents, which we said was 26 milliequivalents of calcium. Now we have to work backwards. So let's convert the milliequivalents of calcium just to the number of molecules of the calcium ion. So we'll multiply the fact that in every 1 millimole of calcium ion, there would be 2 milliequivalents, since the valence on calcium is 2. Milliequivalents cancel, and I'm now in millimoles of calcium. Now, here's a little bit of a trick. We have to be careful. I need to convert from the number of molecules of just the calcium ion to the number of equivalent molecules of the parent compound, calcium citrate. So we have to look at the formula. And if you look at the formula, you'll see that essentially calcium has a plus 2 valence, but citrate has a minus 3. So to get the 2 to equal out, we have to actually combine 3 calciums with 2 citrates. Therefore, the formula is Ca3 and then 2 citrate molecules, meaning that to convert from the number of molecules of calcium to the number of equivalent molecules of calcium citrate, we multiply by the fact that there would be 1 millimole of the calcium citrate, there would be over 3 millimoles of calcium, because there are 3 calciums in every 1 molecule of calcium citrate. Now I am in finally the number of molecules of calcium citrate. To convert it to the equivalent weight, I'll multiply by its formula weight, which we were given at 498.44. Millimoles cancel, therefore, and we're in the weight in milligrams of the equivalent amount of calcium citrate. That's great. We're almost there. But we wanted to know the number of tablets. So we need to multiply by the fact that we were told that in every 1 tablet, they contain 950 milligrams of the calcium citrate. Milligrams of calcium citrate cancel, and we're finally back into tablets. You do all that math, and you see you need 2.3 tablets. So essentially 2.3 tablets is roughly equivalent to the 2 tablets of the Oscal formulation of calcium carbonate. And that answers this question. The next question continues on with our milliequivalent skills and everyone's favorite calcium. And it says, you have 147 milliliters of a 10% weight per volume calcium chloride solution. And in this case, we are using the dihydrate. So I give you the formula for calcium chloride dihydrate, and its molecular weight of 147. And the first letter A part of this question says, calculate the millimoles of calcium chloride, given the volume and the concentration of the calcium chloride solution we have. So let's start with that. What we know is we have 147 milliliters, and then we'll multiply it by its concentration, which we said was 10% weight per volume, which will change to and use the expression as 10 grams of calcium chloride for every 100 milliliters. Next, let's convert the grams from grams to milligrams. So we'll multiply by the fact that there's 1,000 milligrams per grams, and now grams have canceled, and I'll be in milligrams of calcium chloride. And lastly, it wants to know the number of millimoles. So to do that, we simply need to divide by its formula weight. So again, we have we were given the formula weight at 147. So we'll divide by 147 milligrams. Milligrams cancel, and do that math all the way across. And you see that starting with 147 milliliters of a 10% solution, that would give us in the end 100 millimoles of calcium chloride. Part B then says to calculate the number of milliequivalents from this calcium. Well, that's easy from where we're starting at, because we're starting with 100 millimoles of calcium chloride, since we already just calculated that. The next would be to convert from the number of molecules, though, of just calcium ion within the calcium chloride. So looking at the formula, again, there's just one molecule of calcium for every one calcium chloride. So we can convert, and now we're in millimoles of just calcium. Lastly, to convert to milliequivalents, we multiply by the valence, and the valence on calcium is 2, meaning there are 2 milliequivalents of calcium for every 1 millimole of calcium ion. And millimoles cancel, we'll be in milliequivalents, do that math, and we see that that would provide 200 milliequivalents of calcium. And lastly, letter C says to calculate the osmolarity of the solution. All right, so how would we do that? Well, let's start with the number of molecules that we have in our solution. Remember, we've started with our 147 milliliters. We know that that will provide 100 millimoles of calcium chloride. So now all we need to do is take that 100 millimoles of calcium chloride and multiply it by the number of particles that would be produced from each molecule. So if you look at the formula CaCl2, since it's an electrolyte that in water would dissociate, it would dissociate into 1 calcium and 2 chlorides. So calcium plus chloride equals 3 total particles. So we're going to multiply this by the fact that there would be 3 milliosmoles for every 1 millimole of calcium chloride. So 100 times 3 means we would get 300 milliosmoles. But be careful here on this question. It wants to express the osmolarity, which is the milliosmoles per liter. So what we need to do is actually say, okay, if we had 1,000 milliliters, so we'll start with 1,000 milliliters, times the concentration we just determined, which was that you get 300 milliosmoles for 147 milliliters. I'll remind you that 300 milliosmoles represented the amount of milliosmoles from 100 millimoles, and 100 millimoles is what you get from 147 milliliters. So we take 1,000 milliliters times 300 milliosmoles for every 147 milliliters cancels, and what we get is a final value of 2,040.8 milliosmoles. And that was the number of milliosmoles for a liter, which means that's our osmolarity. Our final answer to letter C would be 2,040.8 milliosmoles per liter, and that represents the osmolarity of that solution, which ends question number 4. All right, let's proceed on with question number 5, and it asks, how many milliliters of a 1 to 50 weight per volume strength of boric acid solution can be prepared from 500 milliliters of a 4% weight per volume boric acid stock solution? So this is a dilution. We're wanting to know how many milliliters of a lower strength can be produced from a 500 milliliters of a higher strength. So we have a dilution. And we've also got a problem with our concentrations. They're expressed differently. I have a 1 to 50 and I have a 4%. So clearly we've got a little bit of work to do. But the way that we would approach this question with any dilution is simply with the fact that we know that the concentration times the quantity is going to equal the concentration times the quantity afterwards. Since in a dilution, mass doesn't change. So let's set up our formulas. So we have C1, our initial, what we want is a solution that has a 1 to 50 concentration weight per volume. And we'll have some unknown X milliliters. We don't know how many of that milliliters we're going to have. But what we know is that we're going to prepare that using a concentration that has 4% and a volume of 500 milliliters. So I'm almost ready to do this, but the problem is I've got to get my concentrations in the same units. So let's change our 1 to 50 ratio strength to a percent strength. So I would do that by simply restating the 1 to 50 as 1 gram over 50 milliliters. And then since we want it as a percent, which means grams per 100 milliliters, let's just multiply the numerator and the denominator by 2. So that would equal 2 grams in the numerator over 100 milliliters in the denominator. That's, by definition, a percent. Weight per volume is grams per 100 mils. So essentially, I've re-expressed that as 2%. 2% weight per volume is the same as a 1 to 50 ratio strength. So now what I can do is set up my masses. As mass 1, use my new 2%. So mass 1 is 2% times X milliliters. And my mass 2 is going to be my 4% times its 500 milliliters. And since it's a dilution, we know that M1 equals M2. So I know that 2% times X milliliters is equal to 4% times 500 milliliters. Since, let's double check our units, percent, and milliliters, milliliters. Now I can drop my units and just do the math. So 2 times X is equal to 2X. And that would equal 4 times 500, which is 2,000. I divide both sides by 2, and I see that X equals 1,000 milliliters, which is essentially the answer to this question, which wanted to know how many milliliters of 2% solution can I make using 500 milliliters of a 4% solution? And the answer to that question is 1,000 milliliters. All right. Next question is a little different. Let's read it carefully. It says, a patient has been taking Armour Thyroid 2 grains daily. And so I show you in that picture here, that's a tablet. So the tablet this patient is taking contains 2 grains of Armour Thyroid. He's been taking that once every day. He is now unable to take anything by mouth, and the physician wants to know the volume of levothyroxine injection to be given intravenously to provide a bioequivalent dosage. Okay? So this kind of goes back to some of our pharmacokinetics review when we talked about bioequivalence. Some information you need to be able to answer this question is included that 1 grain of thyroid is approximately equivalent to 100 micrograms of levothyroxine. So that's one thing. Also know that levothyroxine is 75% absorbed from the gastrointestinal tract after an oral administration. Remember how we said that when you take tablets, sometimes not all of the drug can actually make it into the bloodstream. Sometimes it's not completely dissolved. Sometimes the body just doesn't absorb the full amount. So what we're saying in this case, that whatever amount we take orally, only 75% of that dose actually makes it into the bloodstream. And then lastly, the concentration of the levothyroxine injection that we're using contains 200 micrograms of levothyroxine per 5 milliliters. Okay? So, wow, that's a lot of information. In the end, what the question is asking for is what is the volume in milliliters of the levothyroxine injectable that we should use and give as a single daily dose to replace the 2 grains of Armour Thyroid. So, where do we start? Let's start at the end with what we are trying to replace. We are trying to replace what the patient had been taking every day, which is 2 grains of thyroid. Okay? So our first step is to convert the grains of thyroid to the equivalent weight of levothyroxine. And you can use T for thyroid and L for levothyroxine. So what we were told is that 1 grain of thyroid was equivalent to 100 micrograms of levothyroxine. So let's multiply by that ratio. So we'll take 2 grains of thyroid times the fact that on top you get 100 micrograms of levothyroxine for every 1 grain of thyroid. Grains of thyroid cancel, and I now have the equivalent amount, essentially, of an oral form of the levothyroxine. The problem we were also told, though, is that we only absorb 75% of any given dose from the stomach. So now what I'm going to multiply is that by that 75% expressed as we only absorb 75 micrograms for every 100 micrograms that's swallowed. Remember, our 75% absorption means only 75% of a dose actually gets into the blood, which means out of 100 micrograms swallowed, I'm only going to absorb 75 micrograms. So now my micrograms of levothyroxine swallowed essentially cancel, and I now have the weight in micrograms of levothyroxine that would have been absorbed into the blood. That's the dose that needs to be given via an intravenous injection. So lastly, we got to convert that dose or that weight in micrograms of levothyroxine to an equivalent volume of the injectable. So we'll use its concentration and we'll multiply it by the fact that we were told that in 5 milliliters, would contain 200 micrograms of levothyroxine. So finally, micrograms of levothyroxine cancel, and we would have our volume in milliliters. So if we do that math from left to right, we see that we would get a final volume of 3.75 milliliters. That's the volume of our injectable that provides the same amount of levothyroxine that ends up in the blood had we swallowed 2 grains of the Armour thyroid tablets. And that's essentially saying that is the bioequivalent dose. 3.75 milligrams of the injectable is bioequivalent to 2 grains of the oral Armour thyroid tablets. And that answers this question. All right, well, let's continue on with the next question, number 7. And as a little bit of background, it says, a patient needs to receive 2 milligrams of a bupivacaine per day via an intrathecal pump. And so before I go on at all, let's just look at the pictures on the lower right-hand side so you can kind of see what that means. A pump, essentially, this pump contains a reservoir. That is a certain volume of the drug contained within the pump. We're told in this question that that pump contains 50 milliliters. So the reservoir within that little silver disc is a total volume of 50 milliliters. But 50 milliliters of what? We're also told that the solution that has 50 mils contains 0.25% concentration of bupivacaine. So 50 milliliters of a 0.25% concentration bupivacaine solution is placed within that reservoir. Now that pump then is attached with a cannula or a little bit of tubing that actually is threaded inside the person to end up attached to their spinal column so that it's actually injected directly into the CSF or the cerebrospinal fluid. So this is a way to pump drugs past everything that the body does to prevent things from getting into the brain and putting it directly into the central spinal fluid. Okay? So with that as a background then, the first question actually says, what should the infusion rate be in milliliters per hour for this pump? So I'll remind you, the question says, give this person 2 milligrams per day of bupivacaine, and if we're going to use this pump to do that, what should the infusion rate be? Well, let's start with what we want per day, which was 2 milligrams per day. That's what we were told. Let's convert milligrams to grams by multiplying by 1 gram over 1,000 milligrams, so that milligrams cancel. I'm in grams. That's good, because I can use my percent concentration now to convert from the weight of bupivacaine in grams to its volume. So we'll multiply by the fact, based off of the concentration, that in 100 milliliters, there would contain 0.25 grams. Grams of bupivacaine cancel, and I'm in milliliters. That's great. And right now I'm in milliliters per day, though. And the last step would be to tell me how many milliliters per hour. So let's also multiply by the fact that in one day, there are 24 hours. That way days cancel, and my final units would be in milliliters per hour. So if I do all that math going from left to right, my final answer would be 0.03 milliliters per hour. Part B of this question says, okay, well, how many days will this volume of infusion last? If you're going to pump it in at 0.03 milliliters per hour, how long will this reservoir last? Well, that's easy. We know the volume of the reservoir. We were told it was 50 milliliters. So if I take my 50 milliliters times the infusion rate we just calculated, expressed that in every 1 hour, it would infuse 0.03 milliliters. Milliliters cancel, and that would calculate the number of hours the reservoir would last. But the question did want it expressed in days, so once again I've got to convert back from hours to days. So let's multiply by the fact that in one day there are 24 hours. This way my units of hours cancel, and if I do that math from left to right, you can see that the reservoir at that rate would last 69.4 days. And that's the final answer to question 7. All right, our next question, number 8, starts with this, that a pharmacist has mixed 50 milligrams of an experimental drug with 334.5 milligrams of lactose. However, the desired strength is a 1 to 10 ratio strength weight per weight. And therefore, how many grams of lactose should be added to the mixture to provide the desired strength? And I specifically tell you in this question to solve it using algebra or the direct method. All right, so what is this here? This is a dilution. We have a certain concentration, and part of the problem is the concentration isn't very clear. We have 50 milligrams with 334.5 milligrams of lactose, but if you mix all that up, it does give you some concentration. However, the question says it's not the desired concentration because the desired concentration is a 1 to 10 weight per weight, and therefore add more lactose. Or how much lactose do we need to add? this is a dilution. It's made confusing because my concentrations are weird to begin with. So let's start with this, stay calm, and let's come up with some actual concentrations. And I think because it is often easier to solve these questions when our concentrations are expressed as a percent weight per weight, let's do that. So the first thing I suggest to do is let's calculate our current mixture and determine its percent weight per weight concentration. Okay, and that's actually a little bit tricky because I was given the individual parts. I was given 50 milligrams of experimental drug and a certain amount of lactose. So my first thing I need to understand to do is to come up with the total weight. So the total weight of my mixture is, and I'm going to express everything in grams just to simplify the percent calculation. Going back and saying that 50 milligrams of experimental drug is the same as 0.05 grams of that drug. And I'm going to add that to 0.3345 grams of lactose. That's what I was told in the question. If I add those two together, what I'm starting with, what I have already, is a total weight of 0.3845 grams. Now, to express my experimental drug as a percent weight per weight concentration, what I have to do is, you can do a couple of different ways. One way I'll show you here is to set up that proportion, that is, that I have 0.05 grams of experimental drug over a total weight of 0.03845 grams total. Set that equal to X over 100 grams. And I did that because a percent weight per weight is a amount per grams over 100 grams. So now when I solve for X, it would represent the grams. That would be equivalent if I had 100 grams of my product. So if I solve for X, I get 13. And since it would be 13 grams over 100 grams, that's essentially 13% weight per weight. All right. So that's my current mixture. Next, let's do the same thing, determine a percent weight per weight for the desired mixture, because my 1 to 10 doesn't help me. I want to express 1 to 10 as a percent. Easy enough. Let's do, again, 1 gram over 10 grams, which is what I might desire. Set that equal to some X over 100 grams. So again, I can determine the grams, the weight in grams per 100 grams. Solve for X, and I see that X equals 10. Therefore, 10 grams per 100 grams means the same as 10%. So let's start all over here. What this question is saying is, how much lactose do you have to add to a 13% concentration weight per weight mixture of this experimental drug to reduce its concentration to 10%? That makes a lot more sense. So to do this, it said to use the algebra method. So we'll use the fact that our CQ, that our concentration times quantity to begin with, is going to equal our concentration and quantity afterwards, since in a dilution, the mass does not change. So let's set up our C's and Q's. What do I have to begin with? I know that my current concentration is 13% weight per weight, and I know my total quantity. My total quantity I calculated to be 0.3845 grams. Therefore, then what is my C and Q is going to be after my adding the lactose? Well, my desired concentration afterwards, my C2 is 10%. And my quantity afterwards, I don't know it, but I can predict it because it's going to be 0.3845 grams plus some X grams of lactose. And X is what I'm solving for. It's the amount of additional lactose. Additional on top of what I started with was the 0.3845 grams. So now I can set my mass 1 equal to mass 2 and say that the quantity of 13% times 0.03845 grams is going to equal 10% times the quantity of 0.3845 grams plus X grams. Check our units, percent, grams, grams. Good. Let's drop the units and just do the math. So 13 times 0.3845 equals 5. That would equal then 10 times 0.3845. So that equals 3.845 plus 10 times X is 10X. Now I just rearrange that and get that 10X is equal to 1.1455. Divide both sides by 10, and my answer is 0.1155 grams. And that is the answer to this question. That is the weight of lactose I would need to add to my existing 13%. So if I add the 0.1155 grams to my 0.3845 grams of 13%, mix that all together, and basically I get a resulting 10% concentration mixture. And that's the answer to this first part to this question. Because the second part to this question is to answer this same question, but instead of using the algebra or the direct method, we are going to solve it using alligation. That's the good news is that we've already done some of this work. So again, since it's the same question with the same amounts, again, we know that we're starting with a 13% and we want to add lactose till we get a 10%. And I would argue, I'm arguing here. I like the alligation method. It seems like a very straightforward way to solve these questions as well. So let's go set up the alligation. And I'll remind you, we put your high strength on top, which was 13%. Directly below it and down a ways, we put the low strength. And remember, we're adding lactose. We're diluting it. Lactose has a 0 concentration. There is no drug in our lactose. So our high strength is 13%. Our low strength lactose is 0%. And what we're going to put in the middle and slightly to the right is our target concentration, which was 10%. Now, following the alligation method, we'll start on the top left with the 13%, follow the arrows down diagonally to the lower right, and cross-subtract. So 13 minus 10 is 3. So essentially, I need 3 parts of the 0%. Doing the same thing, starting with the 0%, following the arrows diagonally up to the upper right. Again, we'll cross-subtract, so 10 minus 0 is 10. So that says I need 10 parts to be my 13%. The only other question is out of how many total parts, so we'll just take the parts. So we're going to take 10 parts of my experimental drug and 3 parts of my lactose, add those together. The total number of parts would be 13. So again, looking on top there, following the dashed arrows, for the 13% experimental drug that I have now, I'm going to need 10 out of the 13 parts to be that. On the bottom, for the lactose, I can see that I'll need 3 out of a total of 13 parts to be lactose. So where do I go now? I'm still trying to figure out the lactose, but I can't start right there. Because the only other thing I know, if you look at the parts, do parts of lactose, parts of experimental drug, total number of parts. What I know is the weight of my experimental drug. I know I have a total of 0.3845 grams of my 13% experimental drug. Well, that's equivalent to or equal to the 10 parts. So what I can do is take my upper proportion that says 10 parts of experimental drug over 13 parts total, set that equal to the actual weight of the experimental drug I have, 0.3845 grams, over X. And when I solve for X, X will represent the weight of the 13 parts, or the weight of the total combination of lactose plus experimental drug. So when I solve for X, I see that my total is 0.5 grams. That 0.5 grams represents the weight of 13 parts. We just solved for that. So now what I can do is go down to the ratio below for the lactose, which said that I needed 3 parts lactose for 13 parts total. I can now set that equal to some X weight on top for the lactose over the weight of the total, because I just solved for that. I know my 13 parts is going to have a total weight of 0.5 grams. So solve for that, do that little bit of math, 3 times 0.5 divided by 13, and I see that my X, in this case, the total weight of lactose that I need to add is 0.115 grams of lactose. And that's the same answer we got previously using the algebra method, and we've just essentially solved for the same quantity, but using the alligation alternative method. All right, let's get a little more straightforward again and go back to some good old dosing questions, but with a little bit of a twist. So let's start with this question that involves mitomycin, which is a chemotherapeutic drug. And it says, the dose of mitomycin injection is 20 milligrams per meter squared per day. Determine the daily dose for a patient who weighs 144 pounds and is 68 inches tall. Well, that's pretty straightforward, right? Well, the only thing missing here is that the dosing is based off of body surface area in the units of metered squared. And clearly I wasn't given that, but I was given the patient's weight and height, which is all I need to be able to calculate their body surface area. So let's do that first, and then we can actually calculate the dose for this patient. So the trick with the body surface area, I'll remind you, the formula that we use, the most stellar formula, uses the height in centimeters and the weight in kilograms. So we need to convert the values that we were given into those units. So let's do that first for height. I was told this patient stands 68 inches in height. So let's convert that to centimeters by multiplying by the conversion that hopefully you should be familiar with, that there are 2.54 centimeters per inch. I multiply that way, inches cancel, and I'm in the units of centimeters, which would be 173 centimeters. Next, let's do the similar thing for weight. I was told the patient weighs 144 pounds. We need to convert that to kilograms, and that's a pretty straightforward conversion because in 1 kilogram, there are 2.2 pounds. We multiply that out, pounds cancel, and I'm now in kilograms. And so this patient weighs 65.5 kilograms. Now I'm ready to calculate the body surface area. So I'll remind you, the formula for that is to take the square root of the product of the weight in kilograms times the height in centimeters divided by 3,600. So remember to do all of that first and then take the square root. So if we plug in the actual numbers for this patient, we could take their height of 173 centimeters times their weight in kilograms, which was 65.5, divide that by 3,600, and then don't forget to take the square root of that value. And the answer you should get is 1.77, and the units with that formula would be metered squared. Now that I have that was the hard work. To actually calculate the dose for this patient, all we need to do is to take their body surface area of 1.77 metered squared times the 20 milligrams per meter squared per day. And what we can see by doing that math is this patient would require 35.4 milligrams per day. And that's the answer to question number 9. Question number 8 is related, a different question, but similar. So another chemotherapy agent, cytarabine. So this question reads, a patient with a body surface area of 1.5 meters squared is to receive 7.5 milligrams per meter squared per hour of cytarabine. How many drops per minute of an IV infusion containing cytarabine 100 milligrams per liter should be given if the infusion set has a drop factor of 20 drops per milliliter? All right, a lot of information there. We just need to string it together and make sure that our units cancel. This was a very kind of classic dosing information here. We don't have to calculate body surface area. It was already given to us. Well, we've got to go from the body surface area to the dose, and then the dose to the volume, and then the volume to the drops, and all of that. So let's see if we can set it up to make sure that our units cancel. So again, the dose in this case is body surface area base. So let's start with this patient's body surface area of 1.5 meters squared. We'll then multiply that by the fact that the dosing is 7.5 milligrams per meter squared per hour. All right, so we got to keep those in mind because when we multiply that, then our units of meter squared cancel and we're in milligrams per hour. But in the end, we want drops per minute. So we've got some unit conversions to continue to do. Okay, so the first thing is to convert the weight of the drug in milligrams to some volume, and that is going to be based off of the concentration we were given, which was a little weird, but we can deal with it. We were told that this concentration of the solution is 100 milligrams per liter. So we're going to multiply this times 1 liter over 100 milligrams so that milligrams cancel, and I'm now essentially in liters per hour. I don't like liters. We need to get to drops. So let's first convert liters to milliliters by multiplying by 1,000 milliliters per liter. That way liters cancel. And then finally, I can get rid of my milliliters and get to the drops by using the drop factor. And we were told that our IV infusion set has 20 drops per milliliter. So if I multiply by that, then milliliters cancel, and my final units on top will be drops. And we're actually, at this point, I'm in drops per hour. So the last thing is to convert my units of time from hours to minutes, and I would do that by multiplying by the fact that in 1 hour, there was 60 minutes. That way units of hours cancel, and my final units would be in drops per minute, which is what the question asked for. So then if I just do the math from left to right all the way over, my numeric value would be 37.5, and the value and the units would be in drops per minute. And that is the answer to question number 10. All right, question number 11 is a change and back to our kind of dilution aspect. So let's read the question. It says, how many milligrams of sodium fluoride are needed to prepare 100 milliliters of a stock sodium fluoride solution such that a solution containing 2 parts per million of sodium fluoride results when 0.5 milliliters of the stock solution is diluted to 250 milliliters of water? Okay, So there we have it. So this is another kind of tricky dilution question, which is why we're doing these questions, because these are kind of the hard ones to kind of get down. So I'll remind you, in a dilution, we start with a certain mass and we end with that same mass. But what's different is the actual concentrations and the quantities before and after. So let's set up our C's and Q's so we can figure out what our masses are doing. Okay? So let's take a step back in this question. So it's wanting to know, essentially, how many milligrams of sodium fluoride are needed to prepare 100 mils of solution. Well, that's a concentration, but I don't know how many milligrams, so I don't know the concentration. So my initial concentration of this solution is X. I don't know. So let's put X percent weight per volume equal to my initial concentration. Okay? What do I know about that quantity? Well, what I know here is that I'm going to use 0.5 mils of that solution to prepare something else. So the quantity of that concentration I'm going to use here is 0.5 mLs. What do I make with that 0.5 mLs? I make a solution that has a certain concentration. That is, the concentration 2 is 2 parts per million. I was told that's the concentration I will get. And I was told that it's diluted. That's the concentration that results when my 0.5 mils is diluted to a total volume of 250 milliliters. So I know my C2 and Q2. My concentration 2 is 2 parts per million, and my Q2 is 250 milliliters. Okay? And that's what results when I take my initial concentration, which I don't know what that is, but I know that I take and use 0.5 milliliters of that. That's how I get my C2, Q2. All right, so hopefully you can kind of see where the C1s, Q1s, C2s, Q2s came to be. My only biggest problem here is my C2 is still expressed in parts per million, and that ain't going to fly. Let's fix that. So let's get to percents. These are so much easier in a percent. That's easy. Let's just say 2 parts per million means 2 grams per 1 million milliliters. And I know that's an ugly looking number, but all I have to do is set that equal to some X over 100. What I want to know is the proportional amount had it been just 100 milliliters, because that would be the same as my percent weight per volume. So if I just solve for X, it'll be a small number, but I can deal with that. X is equal to 0.0002. And so that would be the number of grams per 100 mils. It's the same as a percent weight per volume. So really, I'm going to now substitute for my C2 essentially 0.0002%. And then I can proceed on, and since I know this is a dilution where the mass doesn't change, I'm going to set my mass 1, which we said is X percent times 0.5 mLs, equal to mass 2, which I now know to be my 0.0002% times 250 milliliters. Let's do a quick double check on units, percent, milliliters. Everything's good. Let's just do the math. So X times 0.5 is 0.5X. 0.0002 times 250 is 0.05. So now all I need to do is divide both sides by 0.5, and I see that X is actually equal to 0.1, and remember X was equal to the percent concentration to begin with. So I know that what I need to do to make this final product is my concentration to begin with has to be 0.1%. That's not my final answer. I need to know that. It's very important. But remember, I'll remind you, the question said, how many milligrams of sodium fluoride are needed to prepare 100 milliliters of this stock solution? I know the stock solution has to have a concentration of 0.1%, and I now remember I need to make 100 mils of that. So how much sodium fluoride do I need? So that's pretty straightforward. All I have to do is take the volume I want to prepare, which is 100 milliliters, times the concentration we just calculated, which was 0.1%, which means 0.1 grams per 100 milliliters. Milliliters cancel, and I'm in grams. Lastly, to convert to milligrams, let's just multiply by 1,000 milligrams per gram, so grams cancel. And the final value when you do that math is 100 milligrams. Wow. That's the end of this question. Yay. What does it mean? It means if I took 100 milligrams of sodium fluoride and I dissolved it in 100 milliliters of solution and stirred it all up, that concentration would be 0.1%. Very good. And if we took basically half a milliliter of that and diluted it to 250 milliliters, that solution would have a final concentration of 2 parts per million, or essentially 0.0002%. It all works. It's a beautiful thing. And more importantly, we finished this question. All right, we're about halfway through this lecture, so I assume by now some of you are feeling a fair amount of pain, so I thought it would be a good time to try to give you a question on morphine sulfate and pain relief. So this question says, the epidural dose of morphine sulfate should not exceed 10 milligrams in a 24-hour period. The reason we need to know that is we're trying to set up a patient-controlled analgesia pump. So a PCA, patient-controlled analgesia, is a pump that allows the patient to hit the button every time they need some pain relief. So if they've got some pain, they hit the button and a certain dose will be administered. Now, again, we don't want them to just hit the button all the time or they'll overdose themselves. So we're going to have a lockout. They can hit the button, but it's only ever going to respond after a 30-minute delay. Okay, so they can give themselves a dose of this morphine every 30 minutes. So long as that by the time they look at a 24-hour time period, they can't have administered more than 10 milligrams. So that's what we know so far. Looking at the specific question, it wants us to use a solution with a concentration of 0.5 milligrams of morphine per milliliter and asks what the maximum volume administered per dose would be such that, again, we don't exceed the maximum daily dose of 10 milligrams. Okay? So this is not a hard math question. It's just a simple question of organizing what we know. So I would tell you to rewrite and let's list out what we know. Let's start with the total morphine dose per day. Remember, we do not want to exceed 10 milligrams. So we can't give a total volume that exceeds a total dose of 10 milligrams. So that's our stop. Now, so we know the total dose will be 10 milligrams, but what are the total number of doses? I know I can have one dose every 30 minutes, but how many doses per day is that? Well, let's just calculate the maximum number of doses per day and just start with the fact that a day is 24 hours. Let's convert that to minutes. You'll see why. So 24 hours times 60 minutes per hour gives us the total of minutes in a day. And we want it in minutes because we were told I can get one dose every 30 minutes. So if I multiply by that, minutes cancel, and I would have the number of doses per day. And doing that math, I can see that if I give a dose every 30 minutes, then for a 24-hour period, I could get a total daily number of 48 doses. So let's just relate those. The total daily dose is 10 milligrams. The total daily number of doses is 48 doses. So if we just set that up as a proportion, that is a total day, I'm going to have 10 milligrams in 48 doses. Then all I need to do is convert the milligrams to the actual volume because I was given a concentration of 0.5 milligrams per mil. So if I multiply that times 1 mil over 0.5 milligrams, milligrams cancel, and I essentially am calculating the volume in milliliters per dose. So if I do that math, I've now calculated that each time the patient hits this button, they would give themselves 0.42 milliliters. And that's the answer to this question for the volume. Let's go on, though, because the second part of this question asks, how long will a 50 milliliter cassette of this concentration, the 0.5 milligrams per mil, how long will that solution last if the patient does administer that maximum dose? All right. Well, that's pretty straightforward. We know that the total volume is 50 milliliters. So let's convert the total volume to the total amount of drug. Okay, so 50 milliliters times the concentration of the morphine is 0.5 milligrams per mil. Mils cancel, and I will be in the total amount of morphine in that cassette in milligrams. Then I can multiply that and convert that from the weight of the drug to the days it will last, because I know I was told the maximum this person can get is 10 milligrams per day. So if I multiply it times 1 day over 10 milligrams, milligrams cancel, and I would calculate the number of days. So if I do that math, I can see that at the maximum rate, that is hitting that button every 30 minutes, means that this, and starting with a 50 milliliter cassette, that cassette would last a total of 2.5 days. And that ends this question about the PCA pump. All right, let's get back to calculations that historically have been a little more difficult for students, and those involve calculating isotonicity. So in this question, it reads, you need to prepare a sterile isotonic solution of a new ophthalmic drug for a clinical trial to treat glaucoma. Okay, so it's a fictitious drug, but we're going to make an eye drop out of this drug. What we need to do is we need to prepare a 1.5% weight per volume concentration solution of this drug. What I know about this drug is its molecular weight is 278 and its I value is 1.8. And I'll remind you, the I value is what we use to describe the dissociation constant. Okay? Now, the solution will also contain 0.4% weight per volume of chlorbutanol, and I give you its E value of 0.24. And the preservative, the chlorbutanol is a preservative, and the boric acid is going to be added as well to make up the difference for the isotonicity. Okay, so we have an ophthalmic solution that has 1.5% of our new experimental drug, 0.4% weight per volume of our chlorbutanol as a preservative, and some whatever amount of boric acid we need to make the final thing isotonic. Okay, first question. What is the sodium chloride equivalent for our experimental drug? Because if we're going to calculate isotonicity using the sodium chloride equivalent method, I've got it for chlorbutanol. But if you remember, you can actually calculate it because I was not given the value for it for our drug. But I was given everything I need to know, which is that its dissociation constant, or its I value, was 1.8. And I say that because we were given the formula before that the E value of a substance was equal to the molecular weight of sodium chloride, which was 58.5, divided by its I value, which is 1.8. times the I value of your substance divided by the molecular weight of your substance. Okay? And we have that. For our experimental drug, we were given an I value of 1.8 and its molecular weight of 278. So if we just plug those values into the formula and go ahead and solve and come up with the math numerically, then 58.5 times 1.8 divided by 1.8 times 278 gives us a final value of 0.21. So what this shows you is we've gone ahead and calculated the E value, or the sodium chloride equivalent, for our experimental drug, and we're saying that that value is equal to 0.21, and that's the answer to letter A. Let's go on to letter B, because now it wants to know how much of our experimental drug and how much of the chlorbutanol is actually needed if we were to prepare 250 milliliters of this ophthalmic solution. Okay? Well, that's a simple concentration question, so let's go back and say that, okay, we want to prepare 250 mils of this solution, and we were told in the question, at least for our experimental drug, that it needs to be a 1.5% weight per volume. That means 1.5 grams per 100 milliliters. So if we multiply like that, milliliters cancel, and I would need 3.75 grams of my experimental drug. Let's do the same thing for the chlorbutanol. We're starting with 250 milliliters, and we were told its concentration was 0.4% weight per volume, 0.4 grams per 100 mils. Mils cancel, do the math, and we would get 1 gram. So we have now calculated the weights of our active ingredients. That is, the weight of our experimental drug per 250 mils would need to be 3.75 grams, and the weight of my chlorbutanol for that same volume would be 1 gram. And that's important information to know because if you go on to question letter C, the third part of this question, it wants to know how much boric acid we need to make the 250 milliliters of our solution isotonic. And clearly the amount of boric acid we will need is the amount that's still left after we consider the isotonicity, or the tonicity rather, contributed by our experimental drug and the chlorbutanol. So that's where we'll need to start off with. Let's start with our drug. Now that we know how much drug we're using, 3.75 grams. What we need to do is convert that to an osmotically equivalent amount of sodium chloride. And we can do that because our first part of this question was to determine its E value, which was 0.21. And remember, 0.21 for an E value means 0.21 grams sodium chloride per gram of drug. So if we multiply it like that, it's 3.75 grams of drug times 0.21 grams of sodium chloride over 1 gram of drug. Grams of drug cancel, and we're in grams of sodium chloride. And that number would be 0.79 grams of sodium chloride. That's the equivalent amount of sodium chloride that mimics osmotically the amount of drug we're using. Fantastic. Let's do the same thing for the chlorbutanol. And again, we're starting with 1 gram, and we're going to multiply it by its E factor, which we were given in the question as 0.24, meaning 0.24 grams of sodium chloride per gram of chlorbutanol. Grams of chlorbutanol cancel, and we have essentially 0.24 grams of sodium chloride. Well, all we need to know now is what is our target. The target amount of sodium chloride depends on our volume and the fact that it needs to have a concentration of 0.9%. So using that, let's start with the amount we're preparing, which is 250 milliliters. multiplied by that concentration, the isotonic concentration of sodium chloride, which is 0.9 grams per 100 milliliters. Milliliters cancel. You do that math. We can see that our target for the total amount of sodium chloride we would need to make 250 mils isotonic is 2.25 grams. That's my target. So let's take that and then subtract the amount we're getting from my drug, which we said was 0.79 grams. Then also subtract the amount coming from the chlorbutanol, which we said was 0.24 grams. And what we've determined is that I still need the equivalent of 1.22 grams of sodium chloride. What am I going to use to get that? Well, I'm not going to use sodium chloride. In this question, we were told to use boric acid. So we were given the E value for boric acid at 0.52, which means 0.52 grams of sodium chloride per gram of boric acid. I can just set that equal to the amount of sodium chloride we need, which was 1.22 grams of sodium chloride over X. If I solve for X, I'll determine the grams of boric acid that is equivalent to, which if we do that math, it equals to be 2.35 grams. Therefore, I need 2.35 grams of boric acid to provide the remaining amount of isotonicity to make my final 250 mils isotonic. And that essentially answers this question. All right, let's do some more questions about altering product strength, just because from my experience, these have historically been more difficult questions for students to answer. And this question is all about the commercial product you see here on the right for the testosterone gel. So testosterone gel comes commercially as a 1.62% concentration. What we want to know in this question is how much just blank gel base, additional gel base without any drug in it, could be added to this 30-gram tube of the 1.62% gel to decrease its strength to 0.75%. So again, we want to dilute this concentration and go from a higher concentration, the 1.62, down to a lower concentration, 0.75, by just adding pure base. Okay? And I didn't specify a particular way of doing it. This question could be answered using either the alligation alternative method or the algebraic or direct method. And frankly, it would be a good practice if you do both. So I'm going to do both for you, and let's see how we could answer this question two different ways, get the same answer. All right, so let's start with the alligation alternative. So in the alligation alternative, what we would do is set up by starting with our high strength on top, which is our 1.62% gel that we already have. That's what we're starting with. And then down below, on the very bottom and down a ways, is what we're adding to it, which is just pure gel base, which has 0% testosterone. Okay, so our original concentration is 1.62% testosterone. On top, down below, way down, is our 0% pure base. And what we're trying to make over in the middle on the right is our target, which is to lower the concentration to 0.75%. So that's our target. So now let's do, starting at the top left and follow the arrows down, we'll cross subtract. So following the arrows down, we take 1.62 minus 0.75. And on the lower right, across from the 0%, you can see the difference would be 0.87. Now, doing the same thing, but going from the 0% and going to the upper right, following the arrows diagonally, we would take our 0.75 and subtract 0% to see the difference to be 0.75. So what I've said is I need 0.75 parts to be the 1.62%, and I need 0.87 parts to be the 0%. But out of how many total parts? So let's add those up. 0.75 plus 0.87 gives a total number of parts of 1.62. So now, looking again at the top, of the testosterone gel I already have, that is 1.62%, I need 0.75 parts out of a total of 1.62 parts to be that. On the bottom, I need 0.87 parts to be the pure gel base out of a total of 1.62 parts. So now where do we go from here? Well, the only other thing we know is that we're starting with 30 grams of the 1.62% gel. With that 30 grams, therefore, would be the same as the 0.75 parts. That's what I was given on top. So what I can do is set up a proportion and say that my 0.75 over the 1.62 total parts is equal to 30 grams, because that's the amount of the 1.62% topical gel that I'm starting with, over X. And when I solve for X, X would represent the weight for the 1.62 parts, which is the total weight of the new combination. So when I solve for X, I see that I get 64.8 grams total. The 64.8 represents the 1.62 parts, which represents the total weight of the gel when I'm done. So now I can go down to the bottom and use the relationship that I have that of the pure gel base. I need 0.87 parts out of a total of 1.62. I can set that equal to some unknown weight of just the pure base, but I know my total. My new total I just calculated for the 1.62 parts would be 64.8 grams. So I can set that over the 64.8. Now when I solve for x, I determine that x equals 34.8 grams, and that represents the weight of the gel base that I would need to add to my 30 grams of 1.62% testosterone. Mix all of that together, and my final total would be 64.8 grams of a gel that has a concentration of 0.75%. So again, the answer to this question is that I need 34.8 grams of gel base. Now, can we solve that? Instead of using the alligation alternative, let's solve it using the algebra method. So to do that, we got to set up our C's and Q's. And so what we're starting with, the concentration of our initial gel, we said was 1.62%. And we're starting with 30 grams of that. So my mass 1, my initial mass is 1.62% times 30 grams. What am I adding to that? I'm adding to that some pure gel base. Okay. Well, there's no drug in that gel base, so it's 0%. And how much of that gel base am I adding? I don't know. That's what I'm solving for, so let's set that equal to x. All right. What do I want to get in the end? What I want in the end, so my concentration 3, I want to be 0.75%. That's the concentration I want. What will the final quantity be? What will Q3 be? Well, essentially, it's going to be the 30 grams I start with plus the X grams of the pure gel base that I'm going to add. All right. So since this is a dilution, mass will not change, because if you look at the C2 times Q2, 0% times X grams is going to be 0. So there will be no change in mass when I add that to my mass 1. So I essentially can say that my mass 1 will equal my mass 3. Okay, so if I set that, I can say my 1.62% times the 30 grams will equal my final mass, or my final mass, which is the 0.75%, times the quantity of 30 grams plus X grams. Let's double check my units, percent, and grams. So let's drop those and just do the math. So 1.62 times 30 is 48.6. And I can say that's equal to 0.75 times 30, which is 22.5, plus 0.75 times x, which is 0.75x. So now I can rearrange that formula and say that 26.1 is equal to 0.75x, divide both sides by 0.75, and x equals 34.8. And remember, x represents the weight in grams of the amount of pure gel base to add. And it's the same value that we were able to calculate above using the alligation alternative method. So we know that this question works, or we've got the correct answer using it in both ways, both the alligation alternative and the algebraic method. Part B of this question is very similar and yet importantly different. It's the same calculations in the same way, but doing something opposite. So let's read the question. It says, how many grams of pure testosterone powder should be added to 30 grams of 1.62% gel to increase the strength to 2.5%? So this is not a dilution, it's a fortification. We are making a commercial product stronger by adding, in this case, pure drug. So we can solve this exactly the same way as we did before, using both either the alternative alligation alternative method or the algebra method. And in this case, I'll do them both ways and see that they're going to work very similarly and yet a little different, since it's a fortification and not a dilution. But so let's set up our alligation. It gets set up the same way, but what's different now is our high strength now concentration is our pure testosterone powder. It's 100% testosterone. So on top to the left, my high strength is 100%. Down below is the concentration of the gel I'm starting with again here, which we said was 1.62%. Now our target is something in the middle. So in the middle and slightly to the right is our desired target strength, which we said is now 2.5%. Now let's solve this the same way as any alligation. Starting with the upper left, we'll follow the arrows down diagonally to the lower right and cross subtract. So 100 minus 2.5 is 97.5. Doing the same thing, starting at the low concentration and working my way diagonally up to the upper right, we'll take 2.5 minus the 1.62 and see that that difference is 0.88. And if we add those two values together, 0.88 plus 97.5, then the total number of parts is 98.38. So again, just looking at what we've said on top, for the 100%, looking at the dashed arrows, of the pure testosterone powder, I need to use 0.88 parts of that out of a total of 98.38 parts. And down at the bottom, it says that of my testosterone gel that I already have at 1.62%, that that represents 97.5 parts out of the total mixture now of 98.38 parts. Okay. Now that we've got those proportions, let's look back at what we already know that we have. We have 30 grams of the 1.62% gel. That's equivalent to what we just said was our 97.5 parts. So let's set up that proportion and say that 97.5 parts of the 1.62% gel over the total parts, which is 98.38, is going to equal to my starting weight of the testosterone gel, which is 30 grams over X. And now when I solve for X, it will represent the weight of the total mixture once everything's been added. So solving for X, my total weight is 30.27 grams. That weight represents the weight of the 98.38 parts. So now I can go back up to my top formula and say that, okay, the 0.88 parts of testosterone powder over the total weight of 98.38 parts is going to be equal then to some unknown X grams over what I just solved for the total weight to be 30.27. Solve for X, and you can see that X would equal 0.27 grams, and that is the final answer. That would be the weight of the testosterone I need to add to 30 grams of my 1.62%, mix that all together, and I'd get a final weight of 30.27, but a concentration of testosterone of 2.5%. Now, let's do the same thing using our algebra. Because now, well, let's just set up the algebra. So what's my first product is testosterone powder. And I'm going to take, so the testosterone powder we said has a C1 or a concentration of 100%. How much powder are we going to use? I don't know. That's X. So our Q1 is X grams. So mass 1 is 100% times X. That's my mass 1. What am I adding that to? Well, I'm adding that to a gel that I know has a concentration of 1.62%. And I know it has a total weight of 30 grams. So I know I'm adding that to a mass that has 1.62% times 30 grams. When I do all that, what do I get at the end? What do I want to get in the end? What I want in the end is a concentration 3 of 2.5%. And I know that the final weight I would get, the final quantity at the end, would be the 30 grams plus the X grams of powder that I add. So 30 plus X is the total quantity in the end. Now, since this is a fortification, mass is changing. So this is an example where mass 1 plus mass 2 will equal our final mass. So to set this up, all I've got to do is take my masses. So I'd start with 100% times X grams, mass 1, plus 1.62 times 30 grams, which is mass 2. And say when you add those two together, you get a final mass of 2.5% times the quantity of 30 plus X grams. Percent, grams, grams, grams. So my units are all the same. Let's drop them and do the math. So 100 times X is 100X. 1.62 times 30 is 48.6. On the other side of the equal signs, 2.5 times 30 is 75. Plus then 2.5 times X is 2.5X. So we just need to rearrange this formula. So I subtract 2.5X from both sides. And on the left-hand side, I get 97.5X. And on the right-hand side, if I subtract 48.6 from both sides, I would say that that is equal to 26.4. Then divide both sides by the 97.5, and my final X value would be equal to 0.27 grams. And I'll remind you, X represented the weight of the testosterone, which we now just said would be equal to 0.27 grams. And that also matches the value we got by performing that same calculation using the alligation alternative method. So hopefully this was kind of a helpful review to kind of see how to do both the dilution and the alligation using both the alligation alternative method as well as the algebra or the direct method. All right, let's simplify things here a little bit and go back to some standard dosing questions, things that hopefully by now you're finding are pretty straightforward. So question 15 says, how many grams of nystatin would be needed to prepare a batch of 350 tablets, each containing 500,000 units of nystatin. And it says there that 1 milligram of nystatin is equal to 4,400 units. And this kind of goes back to the chapter we did about units of activity. Not all drugs are based off of weight in terms of their dose. Sometimes we'll say how much a drug we need based off of its units of activity. And nystatin is just one such drug. Okay? So in the end, we're trying to calculate grams, though, and we want to know grams of nystatin to prepare a batch of 350 tablets. So let's start with what we're trying to make, which is 350 tablets. Let's take one step at a time. We want to make 350 tablets that have a basically weight of what, or a concentration of what? It would need to have 500,000 units of nystatin per tablet. It says 500,000 units each. So we'll multiply this times 500,000 units per tablet. Tablets cancel, and I would now be in units of nystatin. But the question wanted to know grams or weight of nystatin, so we can actually formulate this. So let's multiply by the fact we were told that 1 milligram of nystatin has 4,400 units. So if I multiply like that, units will cancel, and I will be in now weight of nystatin. But I'll remind you it's in milligrams, and the question wanted grams. So let's just convert to grams by multiplying by the fact that in 1 gram there's 1,000 milligrams. So milligrams cancel, and if you do that math all the way over, what we were able to show is that we need to weigh 39.8 grams of nystatin. So 39.8 grams of nystatin contains enough units of activity of nystatin such that if you divide it up evenly into 350 tablets, each tablet would have 500,000 units of nystatin. All right, let's move on to number 16. It says, an elixir contains 40 milligrams of drug in each 5 milliliters. How many grams of drug would be needed to prepare 4,000 milliliters of this elixir? Well, this is a pretty easy question for you, hopefully, at this time. So I thought this would be a good time to use Dr. Harrison's miracle elixir for the lack of common sense, because hopefully you wouldn't need to take it because this is such an easy question. Because all we need to do is take our total volume of 4,000 milliliters, multiply it by the concentration we were told, which was 40 milligrams per 5 mLs. Milliliters cancel, and I have the total weight in milligrams, though. But again, the question wanted grams, so let's convert by multiplying by the fact that in 1 gram there's 1,000 milligrams. Milligrams cancel. Do that math all the way over, and turns out we need 32 grams of this drug. If we took 32 grams of the drug and disperse it in 4,000 milliliters of this elixir, our concentration would be the same equivalent as 40 milligrams per 5 mLs. All right, that was to soften you up to get you back to ones that you probably don't like, which involves acid-base reactions. So this question says, what is the pH of a buffer solution prepared with 0.055 molar sodium acetate and 0.01 molar acetic acid? And I give you that the pKa value of acetic acid is 4.76 at 25 degrees Celsius. All right. We would not, in this course, give you particularly difficult questions in terms of the buffer type reactions using buffer solutions, but certainly we expect you to stay calm and be able to use the Henderson-Hasselbalch formula. So I'll remind you, this is the Henderson-Hasselbalch formula for weak acids, which is what we have since we were given acetic acid and its salt, sodium acetate. So really, all we need to do to calculate pH is to take the pKa and add it to the log base 10, and this is where it gets important, of the concentration of the salt divided by the concentration of the acid. And I will remind you, there's 2 things could go wrong here. First of all, you could not get the acid and the salt values right. You got to make sure you know which value goes with the salt, which value goes with the acid. In this case, we were told that the acid is acetic acid, and its corresponding salt, therefore salt meaning sodium, would be the sodium acetate. The second thing that could go wrong is that you don't use your values as molar concentration. You have to use molar concentration both in the numerator and the denominator for this formula to work. Fortunately, we were given our concentrations both in molar concentration, so we don't have a lot of additional work to do. So let's just set it up by plugging in our numbers. So we could say that pH is equal to the pKa, which we said was 4.76, plus the log base 10 of, remember to put the concentration of the salt on top, and we were told that was 0.055 molar concentration of sodium acetate, and divide that by the molar concentration of our acid, which was the acetic acid, which was 0.01. So if we do that math to begin with, so the log base 10 of 0.055 divided by 0.01 gives you 0.74. That's the value you're going to add to the pKa value, which we started with, which was 4.76. If you add those all together, then the final pH of this buffer solution would be a pH of 5.5. All right, next question. It says, a new drug has a sodium chloride equivalent of 0.23. What is the concentration of this drug in an aqueous isotonic solution? What that means is, how much drug do we need to make a solution isotonic, knowing that its E value is 0.23? And this is a pretty easy question. You've got to start, what does isotonic mean? And this is a key question. What does isotonic mean? Isotonic means having an equivalent amount of sodium chloride to 0.9%. Which means 0.9 grams per 100 milliliters. So in this example, if we just standardize the amount of drug that we need per 100 milliliters, then we would need the amount of drugs that is equivalent to 0.9 grams of sodium, because that's the amount of sodium chloride that makes 100 milliliters isotonic. So that's the amount that we want to find an equivalent amount of our drug. Well, we were told that our drug has an E value of 0.23, and this is the trick to this whole question. That means 0.23 grams of sodium chloride per 1 gram of drug. So if we set that value equal to what we know our target to be now, which was 0.9 grams for 100 mils, over then X, then we solve for X, and we found the equivalent amount of drug, which if we solve for that math is 3.9 grams. 3.9 grams of our drug is equivalent to 0.9 grams of sodium chloride. Therefore, if we put 3.9 grams of our drug in 100 milliliters and dissolved it, essentially we would have a 3.9% concentration of our drug, and we know that concentration would be isotonic. And that answers this question. Next question says, 500 milliliters of a solution of 100 milligrams per milliliter of drug is diluted to 2 liters. What is the new concentration? I certainly hope by now that sounds like a dilution question to you, because that's exactly what it is. And in a dilution question, mass 1 equals mass 2. And to do that, we can say that C times Q equals C times Q. So let's just set those up. And this is a pretty straightforward question. The only little trick to this at all is to realize you don't always have to do everything as a percent. Percents are kind of convenient, but I would argue here there's an easier way of doing it, because the concentrations we were given to begin with is that we are going to use a solution that has a concentration of 100 milligrams per milliliter. Well, let's just leave it like that. So C1 equals 100 milligrams per milliliter. Okay. What quantity of that do we have? Well, we have 500 milliliters of that. So my Q1 is 500 milliliters. So clearly mass 1 is equal to 100 milligrams per mil times 500 milliliters. Now, when we dilute it, what is our new concentration? Oh, I don't know. That's what we're going to solve for. So I'm going to set my C2 equal to X, but I'm going to put the units for X to be milligrams per milliliter so that they're the same as my C1. So C2 is X milligrams per milliliter. But my Q2, I know because it says what happens when I dilute it to 2 liters. So I'll quickly convert 2 liters to milliliters by saying that 2 liters is equal to 2,000 milliliters. So that's my Q2, and let's do a quick check. Q2 and Q1 have the same units in milliliters, and C1, C2 have the same units, milligrams per milliliter. So now, since I'm doing a dilution, I can just say M1 equals M2. So I'm going to say that 100 milligrams per milliliter times 500 milliliters is equal to some X milligrams per milliliter times 2,000 milliliters. Double check that my concentrations are the same and my units of quantity are the same, so I can drop those and just solve it. So 100 times 500 is 50,000. And then I can set that equal to X times 2,000, which is 2,000X. Divide both sides by 2,000, and I get 25 milligrams per milliliter. Okay, or my value is 25. And remember, my X was a concentration in milligrams per milliliter. So my answer is 25 milligrams per milliliter. And that answers this question. All right, our next question reads that the recommended dosage for Somatrem is up to 0.1 milligram per kilogram given subcutaneously or intramuscularly 3 times weekly. Okay, so back up a little bit. Somatrem is kind of a generic name for one of our first versions of growth hormone. It's been kind of replaced with a newer version of it, somatropin, but Somatrem was kind of our initial growth hormone that we used to treat individuals that didn't develop or grow normally. And when it first came on the market, it had the brand name of Protropin. So, and you can kind of see those pictures of those vials down here. So we got this drug, Somatrem or Protropin. It's dosed at 0.1 milligram per kilogram, either subcutaneously or intramuscularly 3 times per week. Okay. Now, if you look on those vials down there, it's supplied as this powder for injection that contains 5 milligrams per 2 milliliters after it's been reconstituted. And 1 milligram of Somatrem was equivalent to of actually 2.6 international units of growth hormone. So remember, Somatrem was intended to provide an equivalent or a form of growth hormone. And in fact, 1 milligram of Somatrem provided activity-wise the same as 2.6 IUs of growth hormone. So a lot of background information there. The question itself says, how many milliliters of Protropin injection per dose should be administered to an 84-pound patient? And how many IUs of growth hormone will this patient be receiving equivalent to that dose? Okay, so let's take all that generic information we were given above and make it patient-specific, because we have, and that's where we're going to start. We have a patient who weighs 84 pounds, and this dose is based off of weight. So for a weight-based dose, we'll start with 84 pounds, but we'll need to first convert it to kilograms. So 84 pounds times 1 kilogram, there are 2.2 pounds. Pounds cancel, and I'll be in kilograms. Now, if we look above, the dosing for the patient was 0.1 milligrams per kilogram. Okay, so we multiply the weight by 0.1 milligrams per kilogram. Kilograms cancel, and I can see that my total daily dose, or the total dose I should give, is 3.82 milligrams. Okay. That dose needs to be converted to a volume of the injectable. So I want to give 3.82 milligrams of the Somatrem, but the volume I'm going to do is times its concentration, expressed as for every 2 milliliters, there are 5 milligrams. That way milligrams of Somatropin cancel, and I'd get my final volume. So clearly what I've shown with this math is that an 84-pound patient needs 1.53 milliliters of this injectable, and they would have that volume injected basically 3 times a week. The second part of this question, though, wanted to know about how much equivalent amount of growth hormone is this patient getting with that amount of Somatropin. So let's back up and remind ourselves that we were giving this patient 3.82 milligrams of Somatropin, and we were told that that was equivalent to 2.6 international units of growth hormone per milligram. So if I multiply it that way, milligrams of Somatropin cancel, and I can see that this dose of Somatropin essentially provides 9.9 international units of growth hormone. We have reached the last question. Congratulations if you're still with me. This one isn't too bad, so let's just kind of do it. It's kind of an interesting one for bioavailability, and it has to do with this transdermal patch of estrogen with the brand name of Climera. So Climera is an estradiol transdermal system designed to release estradiol continuously upon application to intact skin. Now, a couple of things about the patch. Each patch is designed to last for 7 days. Okay. Each patch releases a daily bioequivalent dose of 0.1 milligrams, and each patch contains a total of 7.6 milligrams of estradiol and which includes a certain amount of overfill. All right, last question. What percent of the estradiol dose is absorbed across the skin? Okay. Well, where do we start with that? Well, let's start with how much drug is delivered. I mean, how much estradiol does the patch actually give out in 7 days? Okay, and we'll standardize all this since the patch is designed. All of the doses we were given were for the amount for the 7 days. So in 7 days, this drug is going to release a total, we were told, of 7.6 milligrams. Okay. Well, that's the total amount in there, but that includes an 8% overfill. So that's more than actually is going to come out of the patch. 8% of that dose is not going to come out. It's just there to stay in the patch. So the only amount going to be released essentially is 92% of that total. So if we have a total of 7.6 milligrams and only 92% is released because 8% of it is overfill that stays in the patch, then we've got to take 7.6 milligrams times the fact that there is 92 milligrams delivered out of every 100 milligrams in the patch. That's our 92%. So we really only deliver 7 milligrams from that patch in the 7 days. So in 7 days, we will release a total of 7 milligrams. All right. Now, what about what's absorbed? What is the thing about the absorbed? Well, we were told that the daily bioequivalent dose is 0.1 milligrams. So if that's the daily amount, then we're getting 0.1 milligrams per day, but we said this patch lasts for 7 days. So we got to take 7 days times the fact that it basically provides, or we absorb 0.1 milligrams per day. So that means we absorb total over 7 days, 0.7 milligrams. So the last question wanted to know what percent of what is applied is actually absorbed. So to do that, we'll take the weight absorbed in the 7 days, which we just said was 0.7 milligrams. That's what the amount absorbed is, over the total amount that the patch released over 7 days, which we said was 7 milligrams. So 0.7 milligrams divided by 7 milligrams, then times 100 to express it as a percent, would basically show us that 10% of the estradiol dose that is released from this patch over the 7 days actually gets absorbed through the skin and makes it into our blood system. Okay? Well, that answers this question, and it answers this entire lecture. And hopefully this was a valuable yet interesting romp through the variety of the many different types of questions we have really learned how to solve and answer in this calculations course.